Section 9.5, Alternating Series. In this section, we'll be looking at the alternating series test. This test helps us identify whether series that alternate between positive and negative terms converge or diverge. Now, the assumption with these series is that the term inside of our summation that's not the -1 part of it, the thing that's making can alternate, we're going to be assuming this part of it is in fact positive. So obviously as positive n values go into that, this expression itself is positive. You can double check that to make sure, but that's generally kind of the assumption that we're talking about. And so in order for us to determine if one of these types of series converge, there's two checks. The first one is that it is in fact decreasing. So we want to double check obviously that the n plus 1th term is less than or equal to the nth term. The second piece is that the limit of the rest of the rule, right, the stuff we talked about here that's positive, as long as that approaches 0, and those two things both apply, then we can say that the alternating series does converge. Okay. Now it's important to understand, however, that if either of these things fail, there's different outcomes. So if we discover that while this is positive, if it's not decreasing, then the test is simply inconclusive. We don't know anything. We're going to have to choose a different test. However, if the fact that obviously the limit doesn't go to 0, it diverges, because clearly if it doesn't go to 0, then the nth term test for divergence identifies it to be a divergent series. So based on what part may or may not work, we have two outcomes. Okay, so again, if the nth term test applies, okay, clearly it diverges. If it doesn't, in this case, get smaller, then we're just going to say it's inconclusive, and we'll find a different way to go. So let's try our first example. So here we're looking at obviously an alternating series, because clearly with a -1 raised to an exponent, it's going to be having alternating terms of positive and negative, and this right here is definitely positive for positive values of n. So we definitely have this set up. So of course we need to check, of course, is that the limit goes to 0 and that it is in fact decreasing. Well, the easy one to check first off is that as we let n become infinitely big, what does 1 over n do? And again, notice I'm not looking at this part of it. This idea of it approaching 0 is only talking about this part of the series, right? Not the -1 part. You kind of ignore that. Okay, so in this case, clearly it does go to 0. And then the other part, of course, is that we want to make sure it's decreasing. So again, we're going to be ignoring this part of it and just looking at the 1 over n part, and we want to demonstrate it's decreasing. So when we look at the nth term, and we of course want that to be bigger than the n plus 1th term, okay, the nth term of course is 1 over n. Is it true that that will be larger than the next term, which in this case would be 1 over n plus 1? And clearly when you look at plugging positive values of n this is definitely going to be true, because obviously when you work this thing out, this denominator will always be bigger, making the overall value a smaller number. So because this does apply and this does apply, our conclusion is that this alternating series converges by the alternating series test. Now, one thing I'd like to point out before we move on is that if I was to remove this part of it and simply have the series not alternate and just be 1 over n, this is the harmonic series. So without the alternating, this is actually a divergent series. So I think it's a really important thing to point out that if you take the divergent harmonic series and let it alternate, it suddenly becomes a convergent series. And that's an important distinction that alternating series have, something we're going to talk about in a little bit. So I just wanted to highlight that in case you notice the 1 over n and maybe thinking about a relationship between the harmonic series. Absolutely. If this did not alternate, it would be a divergent harmonic series, but letting that alternating happen, and then this test verifies it actually, when you let each and every other number be negative and positive, it does in fact converge. Okay, let's try another example. Again, we have an alternating series. This is definitely going to be a positive term for positive n's, so let's make our check. So again, the real quick easy one is we'll go ahead and do the limit as n goes to infinity, and obviously working with n plus 1 over n, it goes to 1. So in this case, obviously, that's not equal to 0. So real quick and easy, I can say that this diverges, right, by the nth term test. And this is actually one of the reasons I like to start with this of the two things we're checking, whether it be decreasing or the limit of the term going to 0. I like to do this first because right away, if you can see it doesn't go to 0, then we don't need to do anything else. We can say right away that this is a divergent series because again, it doesn't fit with the nth term test. Now in our next example, things look a little different. And because they look a little different, we might need to do a little bit of algebra just to clean it up a little bit and get a better sense of what it looks like. So what I'm going to do first is kind of rewrite the series just to be looking a little nicer, but more importantly, really look like an alternating series. Our previous two examples clearly had the -1 part of it that showed the alternating, but it also had the rest of it. I kind of want to break that up a little bit. So what I'm going to do here is say that while this is -2 raised to the n minus 1, the denominator could also be looked at as -1 to the n minus 1 times 2 to the n minus 1. So we're going to break that up. So I'm going to write this as -1 raised to the n minus 1. And then we have the rest of it, which is going to be n over 2 to the n minus 1. And by doing it that way, I can better understand what the a of n is, right? What the rule is and what the -1 is. Kind of going back to our previous example, you really want to know what the rule part of it is and what the sign changing part of it is, because obviously the rule part of it is what you work with. So in this problem, by breaking it up here, I can remove the -1 part of it and understand this is what I'm working with. Now, again, right away, clearly for positive values of n, okay, this is definitely going to be, well, I should say 1 and above. This is going to be a positive expression, so we're good there. So let's go ahead and check our two pieces. So the first thing is, let's do our limits as n becomes infinitely big. And here, when I do n over 2 raised to the n minus 1, as we let n obviously get bigger and bigger and bigger, the top and the bottom both go to infinity. So we'll apply L'Hopital's rule. Okay, so the derivative of the top is 1. The derivative of the bottom is 2 times n minus 1 times the natural log of 2. And this time, obviously, as we let n become infinitely big, the top remains 1, but the bottom just gets bigger and bigger and bigger, which clearly takes it to 0. Okay, so that right there is taken care of. The next piece, of course, is that I need to verify that the nth term is, in fact, greater than the nth plus 1 term. Okay, I want to demonstrate that it's decreasing. Now, in this term, it may not be as super obvious because, with the nth term, that is n over 2 to the n minus 1. And the nth plus 1 term is going to be an n plus 1 on the top when I add 1 to n. And then this will just be 2 to the n, again, when I replace the n with the n plus 1. Now, looking at this, I don't think it's super obvious because both the numerator and denominator changed that this is going to be bigger than this. So I think an easy way to do that is to actually simplify and do a little bit of algebra. What we can do is we can cross multiply and work it out, and we'll discover what values of n will make this true. And as long as it works for what we need here in the series, it's going to be fine. So doing that, if I cross multiply, I'm going to get n times 2 to the n is greater than n plus 1 times 2 raised to the n minus 1. Now, the next step I'm going to do is I'm going to gather my n's on one side. So I'm going to divide n plus 1 over here, and then I'm going to take my 2 to the n plus 1 and divide that by the 2 to the n, because I think this is going to be easier for me to understand what's going on. So my next step is I'm going to leave this side alone. However, on this side, I can just rewrite this as because they have the common base of 2, and when you subtract the exponents, you're going to take n minus 1 minus n, which is -1, and 2 to the negative first power is simply 1/2. Now, my last step is to investigate, since I've kind of cleaned this up a little bit, what value of n, again, is going to hold this relationship. So I'm going to cross multiply again and get 2n is greater than 1 times n plus 1. Now, solving for n tells me that n must be greater than 1. Now, clearly in my summation, yeah, that's definitely the values that we're working. So because this relationship is true as long as n is greater than 1, and that's what's definitely happening in the summation, I can go ahead and say that, yes, this is in fact happening. It is decreasing. So, of course, my final result is for this series, this is converging by the alternating series test. Now, the next thing we want to talk about that's a really important concept with alternating series is the idea of absolute and conditional convergence. Now, the idea, of course, is that if you take a series and then take the absolute value of all its terms, so in other words, remove the alternating part of it, if that converges, then what we know is that the overall series itself, even if it's alternating, also converges. Now, the thing about it is the converse isn't true. And the reason I bring it up is we can't just look at the alternating series and then make conclusions about this. We have to go in a certain order. So basically, the definition we want to come up with and kind of reason from this is that if you take this series, right, the alternating series, or any series for that matter, but we're working with alternating series, it is absolutely convergent if the series without the signs, right? If we take the absolute value of it and remove the negatives, if that series converges, the alternating series is absolutely convergent. Now, if we notice that the the absolute value of it, right? The thing that is the series without the signs. If that diverges, it doesn't necessarily mean that the alternating series also diverges. In fact, what happens is if the absolute value, right, so the series without the signs, if it diverges, but the alternating series, when you do allow the negatives in there, if that converges, then we can say that this is a conditionally convergent series, okay? Now, this is a little weird how it's worded. So the way I like to look at it is this. When I see any given problem, the first step that I do is I look at what does the series look like without the alternating part of it. So I look at the absolute value and I figure out converge or diverge. I figure it out. Now, once I do that, if it converges, then what I can say is that the alternating series, then that is going to absolutely converge. Now, obviously, if this diverges, then my next step is to say, well, what do I know about that alternating series? Okay, if I do the alternating series test and it diverges, then it diverges. But if this converges by the alternating series test, then I can say that it conditionally will then converge, okay? So I think the best way to tackle these situations when they're asked about absolute versus conditional convergence is the idea that if the absolute value series without signs converges, then clearly we have absolute convergence. If it doesn't, then check about using the alternating series test for conditional convergence. That's the kind of way we want to look at it. So to illustrate this, let's look at this example, okay? Now, obviously right here, I have a kind of weird looking series. It's definitely alternating. And what I'm going to do is I'm going to go ahead and say, what does this look like as the absolute value, okay? And what I mean by that is I'm going to look at the series where I remove the alternating piece of it. So in this example, it's going to go from 1 to infinity, and it's simply going to be 1 over the square root of n. Okay, so when I take the absolute value, I'm just removing the idea that we have negatives and positives. It's all positive. So I'm going to figure out, is this convergent or not? If this is convergent, then this series is absolutely convergent. Now, if this works out to be divergent, that doesn't mean necessarily this is divergent. It could work in the alternating series test, and if that's the case, then I will have a conditionally convergent series. That's the difference, okay? Now, looking at this one right away, I can tell it's a p-series. And in this one, the p-series, right, has a p of 1/2. And since that's less than 1, this diverges. Now, again, my conclusion is not going to be the overall series here diverges. It just means that it's not going to be absolutely convergent. So my next step is, okay, let's take my absolute my series, I should say, without the absolute value, right? Let's take this alternating series and do the alternating series test. Now, as always, if you ignore the negative part of it, this rule part of it is, in fact, positive for, positive values of n. So let's go ahead and check what we need to. So first, let's do the limit as n goes to infinity, right? If we're looking at just the rule part of it, this does go to 0, so that's good. The next thing, of course, is we got to check that it's decreasing, right? So we're going to check, is the nth term greater than, did that the wrong way, is greater than the n plus 1th term. And again, this is pretty cut and dry because clearly the denominator here will be bigger than this one, making the overall smaller, right? So that's definitely going to be true. So even though the absolute value diverged, when I applied the alternating series test, it did pass. So my conclusion here is that this is a conditionally convergent series. Okay, let's look at another example. Again, my first step here is let's go ahead and figure out what the convergence is of this series where we take out the sign. So it's just going to be n squared over n plus 1 squared. Okay, so we're going to figure out what that one's doing. Now, the first thing I'm going to notice right away, of course, is that in this case, if you take a look at that, if I take the limit as n approaches infinity of the term, it definitely does not go to 0 and therefore diverges. And obviously because that diverges, I'm going to go ahead and check the alternating series test. But let me just say, if I was to do the alternating series test, this would also be the first thing I notice. So it fails that as well. And since it fails both, with the absolute value and also fails the alternating series test, this diverges. Okay, now in this example, same thing. The only real difference on this one, we happen to be starting at 2. Not that's a big deal or anything, but we're going to check that out. So the first thing is, let's figure out what this one's doing. Okay, so I'm going to be looking at the series from 2 to infinity. And if I remove the signs, it'll be n over n to the third minus 5. So what I'm going to do is investigate again whether or not this is convergent. If this is a convergent series, I can say the original here is an absolutely convergent series. If this diverges, I'll apply the alternating series test to this just to see if I can get conditional convergence. Now, looking at this, I feel like it looks pretty polynomial, and I think a direct I should say, let's do limit comparison test. I think that's really easy since it looks like a polynomial. Okay, so obviously in the limit comparison test, we're going to compare to a known series, okay? And the known series that I'm going to compare it to is going to be, if I look at this one and simplify it, 1 over n squared, right? Which, by the way, is a convergent p series, because obviously the p is equal to 2, which is greater than 1. Okay, so that means if I can do the limit as n becomes infinitely big, and if I take the n over n cubed pi is 5 and divide that by 1 over n squared, as long as this limit is a positive real number, right, and that means that they both do the same thing. So since my comparison obviously is convergent, if this works out, this is convergent, and more importantly, my alternating series is absolutely convergent. Now, if I go ahead and rewrite my complex fraction, that's going to give me, I still have n to the third minus 5 on bottom, but the n on top ends up being multiplied by n squared, which leads me to 1, which is a positive real number, and therefore I can say that this converges. And since the absolute value here with it converges, then my conclusion here then is that this right here absolutely converges, or I should say it converges absolutely, or however you want to say it. So this is absolute convergence. Okay, let's do one last example. Now, in this one, obviously, as we take a look at it, we're going to be looking at what the general overall idea does. So we're going to look at that absolute value one. So that means when I remove the sign, okay, it's just going to be 1 over 3n. Now, what I notice right away, though, is this diverges. And I know that because this is the harmonic series. I realize there's a 3 down there, but that's no different than just multiplying the harmonic series by 3. It's also, if you want to look at like a p series of 1, however you want to say it, it's the harmonic series. It diverges. Now, again, that doesn't mean necessarily that this diverges. If I apply the alternating series test, and of course it passes, I can say that this conditionally converges. So we're going to check that out. Now, the first thing, obviously, is we'll check our limit. So let's do the limit as n becomes infinitely big of our rule. And clearly that goes to 0, so that's good. Now we're going to take our nth term and see, is that greater than our nth plus 1 term? Now be careful, because this will be 3n plus 3. And I know that because we're replacing the n with n plus 1, and certainly multiplying by 3 generates this. Now clearly, looking at these two fractions, this denominator is bigger, making this smaller, and therefore I can definitely say that it is decreasing. So while it is true the absolute value part of it diverges, because it passes the alternating series test, that means that this series here can conditionally converge. Now, the last thing we want to talk about is what's called the alternating series remainder. This is an important aspect of alternating series that can actually help us understand how good or bad our approximations are going to be. Now, the definition says that if you have an alternating series that is decreasing, and that was something we checked before, then the absolute value of the remainder, right, so basically how big the remainder is, whether it's positive or negative, that happens when trying to actually approximate the sum using n number of terms is always going to be less than or equal to the first neglected term. That's kind of a weird way of saying it, and even looking at the symbols, that doesn't look great, so here's the better way to say it. If an alternating series converges, so as long as we know it's convergent, then the error, right, the amount that you're off by in calculating the value of the series using n number of terms will be no more than the n plus 1th term. So in other words, if I use 6 terms, right, to generate a series, and I know that it is a convergent alternating series, then if I'm wondering, gosh, these 6 terms, if I add them together, how close is it to the actual overall infinite sum? Well, just look at the 7th term. Look at that very next term. However big that term is, I know that my estimate is within that amount. I am not that far off from whatever the actual series is, okay? So that means, back up here in the notation, the actual sum of the series, right, if I subtract what my approximate is, will always be within the very next term. That's the better way to look at it. The remainder, if you will, won't be bigger than the next term. So again, if I use 10 terms to approximate the series, and I'm wondering how good was that, well, I'll look at the 11th term, because however big the 11th term is, that's the most I could possibly be off from the actual sum. Now again, we're assuming in this situation that it is a convergent alternating series. So you can't just jump into this necessarily without knowing that it is alternating, it is convergent, but then this does apply. Okay, so let's look at a couple examples of using the alternating series remainder. Now, in this case, what we want to do is approximate what the actual infinite sum of this series is, but we're going to be using the first 6 terms. And then when we do that, we're going to talk about how accurate that may be and figuring out exactly what that's got to be between, okay? So, first off, we need to verify that this is, in fact, an alternating series, which clearly it is, but we also want to make sure that it is convergent. So we'll simply apply the alternating series test. So the first thing, of course, is to check what happens as we take the rule and let n become infinitely big. And clearly, with this situation, it is going to 0, so that checks out. The next thing, of course, is 1 over n factorial greater than 1 over n plus 1 factorial? And again, that's pretty obvious. The denominator here is bigger than this one, making that smaller. So I can definitely say that checks out. So we do know that this is a convergent alternating series. Okay, so that being said, what we want to do, of course, is figure out what this is going to be. So for my sum, I want to approximate using the first 6 terms. So if I plug 1 in, we get 1. And then if I plug 2 in, we're going to get negative 1/2. Remember, it's alternating. So in this case, because I'm using n plus 1, the odds are going to be positive, the evens are going to be negative. If I plug a 3 in, right, the third term is going to be a positive 1/6. If I plug a 4 in, that's going to be a negative 1/24. Plug a 5 in, it'll be positive 120. And I plug a 6 in, it'll be negative 720. Okay, so if I go ahead and plug those in and punch them up, that's going to give me a 91 1/44. Okay, now to give you a little idea of what that looks like, this is a 4 by the way, that's approximately 0.632. Now obviously, because I've only used 6 terms to figure out what this infinite sum is, this is not the exact answer, but using the alternating series remainder, I'll be able to figure out how close it is. Now, if I'm wondering, gosh, how close is it going to be? Well, all I need to do is say, what's the 7th term? So I'm going to say, well, what's the next term in the series? Remember, I did the first term through the 6th term. What would the next one be? Well, if I plug in 7, right, that's going to give me 1 over 5040. That's the 7th term in the series. And by the way, had that been a negative number, remember, we just take the absolute value of it. Because this is, just giving us a distance away. So even if I had chosen, 5 numbers and the 6th number would be, negative, you do take the absolute value of it, okay? So I'm just going to say, because the 7th term is positive, that's what it is, but technically, you take the absolute value of it. And so this right here tells me roughly how far I'm away. Now, as a decimal, 1 over 5040 is approximately 0.0002. So what I can say is this number, is it close to the actual sum? Yeah, well, actually, this is how far off it might be. So it's actually a pretty good approximation. And in fact, if you wanted, you could actually kind of bound where the actual sum is going to be by saying, well, if I'm off by this much, that means the actual sum is either going to be this much more than my approximate or this much less than my approximate. So what we could say is the sum of the series, whatever it may be, is going to be bounded by, so it's either going to be bigger than or less than these numbers. So I'm going to take how far off it could possibly be and add or subtract it to this number here. So if I subtract 0.0002 from this number, that's going to give me 0.6318. So that means it's got to be bigger than that, or at least that number. If I add 0.0002 to my estimate, that's going to say it's going to be at maximum 0.6322. So even though I don't know exactly what the sum is, because my approximate can only possibly be this much off, that means I must be somewhere between these two values. Now, in our last example, we're going to use the alternating series test to, instead of talk about how close it could be, determine how many terms I should choose to make sure the sum of a series is at least this accurate. Okay, so I don't know how many terms I need, but I want to pick enough that when I plug them in here and add them together, I know my answer has to be at least within, in this case, 1/10,000. So I want to be within 2 decimal places or 3 decimal places here accurate. So to make that happen, the first thing we have to think about is what does that next term look like? Okay, so what I want to talk about is, first off, we want to talk about the n plus 1th term. Now remember, my answer is going to be n terms, right? How many terms do I choose so that my answer is this accurate? Well, that means I need to figure out this value here, talk about the next term, right? The first one I don't use, and that has to be a certain value, okay? Now, first off, when we talk about the next term there, for this example here, again, we ignore this part of it because it doesn't matter, it's absolute value. So it's going to be 1 over n plus 1 squared, okay? Because again, I'm going to replace the n right here with the next term. And I'm letting capital N just be the number. I don't want to let it be the, the index. But but when you plug numbers in, this is what they look like. We don't worry about the sign. We're absolute value them, but this is the next term. What we need about this term, of course, is that it has to be, whatever its value is, right? It has to be within our margin of error. So in this case, we need it to be less than 0.001. And if that's the case, then this number here means that's the number I need to make sure I'm as accurate as possible. So if we want to go ahead and solve, we can cross multiply if we go ahead and write this as a fraction. So 0.001 is going to be 1/1000th. And then, of course, by cross multiplying, it'll be 1,000 is less than n plus 1 squared. So, of course, in order for us to figure it out, we're simply going to, square root and subtract 1. Now, when I do that, it tells me that n must be greater than approximately 30.623. Okay, and again, I just square root of both sides, subtracted 1. So because I need the number of terms I choose to be greater than 30.621, that means the answer to my question is I need 31 terms.